Today I want to try to build an algorithm for generating a maze automatically. And I already took a look at the Wikipedia page for maze generation algorithm. And we're just gonna go with the first one, randomized depth first search. This diagram here, or this animation, let's look at that. Basically illustrates it quite well. You randomly, well, maybe not that one, but you kind of randomly go through points in kind of a depth first search manner, and each point you visit, you remove a wall that would take you to that grid cell. And yeah, let's try to do that and see if we can make that make sense. I didn't really read so much of this, just basically this is all I know, randomized depth first search. So we're gonna try that. Let's start by zooming in a bit, and let's make a new folder. We start a session. We open up new vim, go here, and we will let's disable Copilot for this one, and we're going to use C just because, and here we are, we got that going. So now I usually use this kind of like run script, and we'll do like that. We'll compile it to a file called an executable called main, the file main C, and then if that works, we run it. So let's try this, and we are running. So we can also just do it like this, and hello maze, great. Now I want to use Raylib to kind of get a nice visualization going. And Raylib kind of works like this. Let's also define, say, a width and a height. And we're gonna get that width and height, and we'll call this maze generator. Then at the end we should close the window, and we need to organize a main loop. I think this is the function. I'm going to say begin drawing, end drawing, and in between we can say clear background and make it black. Why not? And let's draw some text at like, I don't know, 100, and the text will be maze. Amazing. And I think we also need font size and color. So let's try that. So if we try to run that now, we cannot include this file because we need to add an include folder, and I have it here. And because I kind of built it in a weird way, we also need to say that this is the place to link. And then we can link to Raylib. And this is not gonna work because, as you can see, there's a bunch of undefined references, so we need to link to some other stuff. And I believe if we do something like this, that should be almost enough. Right, and actually draw text, there's also a problem with that. It should be in this order. And we're trying to link to GLFW. Do we have to do that? No, it's not that. It is a dynamic load. That's what it needs. Okay. So here we are. We have a kind of starting thing. Right. So what are we trying to do? We're trying to make a maze, and I think it would make sense to first define what even is a maze. And it should have a width and a height. That's going to be basically the number of cells it has in the X and Y direction. And then we will have something like walls to the right. It will be some number of them, and walls that go downwards, if that makes sense. So let's say we have a grid. Here's a grid. Then it's possible to have a wall here. That would be a right wall for this grid point, and it's possible to have a wall here. That would be a down wall for this one. So also, for example, for this point there won't be a right wall, and for this point there won't be a down wall. So let's see if we can get this working. So let me include std_bool, and let's try to initialize a maze. Because I want to put this on the top, because usually that's a good idea when you use Raylib. Okay, so here's our maze. What should the width and height be? I think we'll just make it square, and we'll make it 10 by 10. So we'll say width and height is height. And then we are gonna say the right walls will be something we haven't defined yet. Oh, and the same thing for the down walls. So let's get this thing going. Right walls is something that we allocate. Let's allocate it to, let's do it with C_alloc, so everything is 0 to begin with. And how is it this works? I think, well, I think we can do something like this. So we have here C_alloc has the number of members and the size in bytes of that thing. So what we're going to do is, this one we can close. How many do we need? We need width times height. And what is it we need? We need a boolean. And we can just repeat that for the down walls. And let's try to run this. It didn't work because I have this thing. Okay, so that works. But now let's try something where we say, like, for I equals 0, I less than height. Well, I actually kind of prefer this is the width, and then we call this one j less height. And we can say random number is rand modulus 2, and if r equals 0, then maze right walls then we set that one to be active. Then we can repeat that, but just for the down walls. This is just so we have some non-trivial data in this thing. And now let's make a function called drawMaze. I think that makes a lot of sense. Makes a lot of sense. So actually the way I usually like to do it is I also take a rectangle, which is where to draw it, what kind of space is allocated for it. So let's make a rectangle for the full window, and that's going to be 0, starts at 0, and the width is the width, and the height is the height. And then we can allocate some space for the maze. And maybe we want some margin, which we'll define later. And then the width will be the window width minus 2 times the margin. And the height will be the window height minus 2 times the margin. And these are floats actually, so let's do this. Just, it shouldn't matter, but just I like to have it. So let's say that the margin is like 20. I think that's fine. Let's go with that. So now when we draw the window, we should also provide, draw the maze, we should also provide the maze window. Okay, so here it is. Let's start by drawing a rectangle that kind of encompasses the full maze. So something like this, and we can make it white. And I think we need stdlib for some of these functions that we called. And this is spelled wrong, so we do like that. Okay, and here we have the maze. Not drawn yet, but you can see how it works, and we can add like some more margin, it becomes smaller, and everything is nice. Now let's draw all of the walls. So to do that, we're gonna say j less than maze dot height, j plus plus. Right, and as we said, the rightmost element doesn't have a right wall, so we need to check like, is this less than width minus 1? And maze right walls I plus j times maze dot width, because we don't care what's on the last spot, so ignore that. And if there is, then let's draw a line. Let's draw a line. I think it's called just a line. It would make a lot of sense, but let's just check. Yeah, we have draw line. And where should we draw it? So what is the x of this point? It has to be an integer. So everything should be offset by the start of the window the maze is allowed to be in. And then there should be something like a cell size, or let's say cell width, because it doesn't have to be square. And then times I. And the y is the same thing, but it's height and j. Right, so then we have the starting position. Starting position is gonna be, that's gonna be x. Start position y is also gonna be just y, and the end position x is actually also gonna be x because it's a kind of a vertical wall. And this is going to be plus cell height, and the color can just be white for now. So I think that should do it, but now we need to define cell width and cell height. So cell width, and this one, maybe I want to make, well, it shouldn't, a little bit torn, but let's make it a float. So we keep things float for as long as we can. Okay, so we have this amount of space available, and we need to fit this many things in. So this seems like a good place to start. And here we go. So let's try to run that, and it did not work. It actually kind of crashed, which is weird. Because we said j here, so that's why. Okay, now we have a bunch of right walls. Very cool. And actually, we need to do this. Okay, now it's working. because x0 is here, or like I equals 0 is here, and then that's this first cell, so we would have to draw here and not here if there was something there. So let's repeat this exercise, but now for the down walls. And this time the line is actually starting at x, but it's starting and here we have an issue. This should be width. But it's starting down there and it ends up here and still here, and it's the white color. Okay, so now we have some initial walls, but obviously like this is not a good maze because there's a lot of disconnect components, and the algorithm we're gonna implement won't have that. So actually, just to have a starting point, I wanna do this, enable all walls, and I think we can just do memset of maze right walls, and let me see how this one works. So you take the pointer, this is the pointer, you take the value is going to be 0 equal to, which is the same as false, and then how many bytes. So we need Boolean bytes, and then we have to calculate number of cells. Which is this. We do the same thing, but for the down walls. Let me close this thing, and now we can kind of get rid of this, and then we'll say enable all walls of the maze. And if we, right, so actually I made a little bit of an oopsie doopsie, because it's like this. Okay, now we have all the walls, and we can even try to up this a little bit. Let's try to make 100, and now we have a nice grid. Okay, but we'll start with 10 to make it clear what's happening. Okay. Let us now so what we're going to do now is we're going to start somewhere, and we'll start up here for why not. And to do that, I want to keep track of where we are with a new structure. So I will just call point. So if we go back here, let's make a new thing that we'll call current, because it's gonna update. So it starts out as 0, and then we will, let's draw a circle at, of course we have to offset it, and then we have to say, we actually kind of need to know how big the cells are as well. So I'm just gonna copy paste a little bit. So there we go. And so this is the width of the cell, then we want like circle radius, and we're just going to use the width divided by 2, and the circle is going to be placed kind of in the middle of the cell. Right, but something we should not forget is that we need to say times current x plus current x times cell width, and here we need to say current y times cell height, and then we need the radius, I think, and then we can make it, let's make it gold. So here we have a square up here, a circle up there, and if we change this to, let's say 5 and 5, it should go kind of to the middle. Okay, so that's working, and now we're back. So the core of the algorithm is to wherever you are, you take a random step in one of the 4 available directions. So maybe just to encode that, let's go to the top where we have the types, and let's say we'll come up with some directions, which I think we don't need that, so let's say left. Actually, I cannot remember if you need the semicolons when you, no, you don't. So in here it's supposed to be that, and I accidentally had the same thing twice. So here we go. So basically what we want to do is, let's say if is key released, key S for step, then we are going to say, so later on we'll have some restrictions. For example, we don't want to, later on we don't want to visit already visited points, because if you do that, then you'll just end up removing all the walls. So that means you can get into a dead end. So it can actually fail this thing. But let's do something like this: one step, and we will need the current point, and we'll select a step in a random direction. And I do believe we will also need the maze. So let's go ahead and say one step, it takes a maze, and actually it returns Boolean whether it succeeded, and it also takes a point which may be modified. So we will modify it if everything succeeds. So true down here. Now, this is supposed to be a step in a random direction. So let's go ahead and say directions is up, down, left, right. If you do it like this, and you just like loop through these directions and find the first one that you think is okay, then it'll be heavily biased towards always going in the up direction, or always going in the down direction. So that's not so good. And what we need to do is actually shuffle the directions, and there's 4 of those directions, which is probably good to know, because then we can write this function here. This is like a super simple algorithm for shuffling things. And what you do is you loop over the array, you select a random index, so it's going to be random, but it's only of those that are left. It should be like this, and then you shouldn't forget to say, so what are we doing here? First we're saying of those that are left, so we take a random number. Let's say that we have, like, here we go, 2, 3, 4, 5, 6, 7. So we'll have I is like 2, so we're here. Then length minus I is 7 minus 2, that's 5. As you can see, there is 1, 2, 3, 4, 5 left. So we'll have a random number between 1 and 5. Actually also including 0, so we have actually 0 to 4 is what we'll have, which is nice with respect to zero indexing. And what we're going to do is we're going to swap. So let's say that the one we get is 2, but then we add I, so we go 2 up. So we have these two, and then the result is supposed to be this. We swap those two. Okay, so let's do that. Let's save that one. Then we can override that, and we're going to override it with the shuffle index. And then at the shuffle index, we're going to put this temp thing. And that's it. Super simple. That's how you make a random shuffle. Let's just check that it works. So here are some numbers, which could be 7 random numbers. Let's see, random shuffle, the numbers and the 7. We are gonna loop all of those, and we'll print it. We're gonna say something like this, and then we'll just return. So we'll run it a couple of times and see what happens. So let's open a new one here, and okay, we need string because of reasons. So let's go back here, because we're using memset, and for some reason memset isn't strings. And I forgot something, which is I want a new line at the end. Okay, but you can see it's always generating the same thing, and that's because we shouldn't forget when we're using random numbers to see them. And also the built-in random number generator is not very good. And we also have this time thing. I think it's just in time.h, but I'm not too sure. Okay, that works. So now you can see we're getting a different order almost every time. So that seems to be working. So back to this where we try to take a random step. We take the directions, we do a random shuffle, and then we loop through them. So I is less than 4, I plus plus, and what is the chosen direction? That is this one. Then we should check if that is free. And the way I think we're going to do that is with kind of a switch thing. Because if the direction is equal to up direction, we have to do something. If it's down, we have to do another thing. If it's left, we have to do a third thing. And there we go. But you can see what happens. So, well, let's do one. Let's do one case. I think I'll just put that in there. So, what is the candidate? Let's call it the candidate. That is current x. We're going upwards, so that doesn't change. And then it's current y, but -1. Then maybe we can define something to check. So let's call it inbounds, and it will take a maze. Why not? Minor point. And then it should check basically. So point x should be greater than 0. Point x should be less than maze.width. Point y should be greater than 0, and point y should be less than maze.height. Now we can simply do this. Okay, so if we are inbounds, then this candidate is actually good enough. So we'll say, actually, whatever was in current, just overwrite that with candidate and then return true. If it's not inbound, then we break. We go to the next step in the loop, and we go to the next randomly chosen direction. So I think that's quite a nice way to do it, and we can almost copy paste this stuff, which is always nice. Okay, so when we go down, it's instead plus. When we go left, we actually decrement x instead of y, and here it's plus. Now what happens if we go through the loop and we don't find any valid point? So right now there will always be a valid point because we cannot go outside the maze, but later on there won't be a valid point. So at sometimes we will go through the loop where we test all the different directions and we won't find a valid spot. So if we don't do that, we'll just return false. So now we have that. Let's see how it works. And it did not work because I forgot that current is a pointer. So here we go. That should work. Now if I press S, nothing happens. Nothing happens. Because, no, we do call it. Thought we didn't call it. Let's say succeeded. And I guess we can do it as string, and then we can say succeeded, true, false. Let's go over here. And for some reason it doesn't succeed. That's interesting. So probably there's something wrong here. But that looks... So just to debug, let's say checking x, y. So at least a few of those should be good. So what is the maze? It's probably something very obvious that I just cannot see right now. Width, height, that's all good. So then let's call this one result. We're returning true, right? Yeah. So that's not it. Up, down, left, right, that's fine. So why is this one false? Ah, it's because x greater than 0. It should be greater than or equal to. Okay, now I get it. Turn that thing, and now you can see it running around some random direction. Okay. So that's great. That is great. That is very great. I think we had another print here. Let's get rid of that. Now let's try to keep track of the visited points. But to do that, we kind of need some, or at least I would like, some kind of convenient thing that we will call point list. list, and it's gonna have a bunch of points which we'll call items, and it will have a count and a capacity. And then we can say here, let's say point list, make list, and it'll have a capacity, and point list. But first we need to say items is I kind of forgot how, okay, so I kind of forgot how it works. Let me just check. Number of members and size of the members. Okay, so this is how many we want, and we want size of point. That's it. So now we can make a kind of a list quickly. And I'm gonna, so actually you can, if you have a structure like this, as something I've seen sorting do, you can define this convenient macro, which will take the array and an item, and it's going to do a do while loop. We don't need that, I think. And if array, this is assumed to be passed by pointer, so if the count is greater than or equal to array capacity, then you do a quick little realloc. So you'll say array capacity times 2, and then you'll say array items is realloc. And now I have to remember how that one works. So realloc is the pointer to the thing we want to resize, reallocate, and it should be this capacity. And then we can also just do a quick assert that this thing is not null. And I think that means we're gonna need assert.h. So that's great. And then once we've ensured there's enough space, we can say items and the count, and we'll do this and we'll do that. Great. And now we have to remember to take the end of the line and do that. So this is quite a convenient macro. Then you just have a dynamic array, and let's do a point list. So here, this is going to be the visited points. So we'll make a list, and it should have width, let's say maze.width times maze.height. So it has enough capacity to store everything. So we actually don't need the dynamic array part, but you know, whatever. Okay. Now, I actually want to store the old one, I think. So we'll say the old one, we just do a quick copy of that. And if we succeeded, then let's append to the visited points the old one. And then we can also draw those. So let's say for int I less than visited count. Let's go ahead and calculate the x coordinate. So actually first let's get the point out, because that's going to be a bit nicer. It's going to be point x times cell width plus maze window.x, and the y is going to be almost the same. And actually let's add a bit, well, I think we'll need a bit of margin, but let's start with this. We'll draw it there, we'll draw it here, sorry, height, and maybe we'll make it blue. We like blue, and cannot do that, you have to say .items. So here we go, now you can see we draw all these nice squares. So actually, because the circle is drawn before it gets the rectangle comes above, so now you can see the circle is always drawn last, so you will always see that. But I don't really like that these blue rectangles overlap with the walls and so on, so let's add a bit of margin here. So I'm going to make let's call it margin, and we'll just make it 4. So we'll add that margin. We'll say minus margin times 2. And now it's not a huge margin. Let's ramp it up a bit. So now we can just, it looks a little bit nicer, I think. So now let's add another check. Now we have track of what we have visited. So let's make it so that we actually don't ever visit something more than once. So let's say visited. Let's include visited in this here function. So now it's not enough that it's in bounds, but we also have to say not list contains, and we're going to give the visited, and we're going to give the candidate. So we haven't defined this function, but basically we have to check the list and see that this candidate is not in there. And that should be true always. Here we go. So what is list contains? List contains, it takes a point list and it takes something that it's looking for, so I'll just call it needle, and then it just simply looks through the list, and then we have to say if, so here we have we call it hey. Why is it colored like that? Hey, okay, good. So it's this item, and if hey x equals needle x and hey y equals needle y, then we can return true. Otherwise we have to keep checking. If we never find it, we say false. So let's have a look at what happens now. So you see we never actually go on top of anything we've hit before, but soon we will see something. Okay, now we cannot go anywhere because we're in a dead end. We're surrounded by blue squares. And what you do in this case for this algorithm is you backtrack. You backtrack to the last, you backtrack one step and then you try again to see if you can find a way out at that point. Now to backtrack, I want to keep a path here. Whoopsie. Oopsie. The path is supposed to have all the things that we have visited. So I think it makes sense to do a little bit of an append here, and we'll append the old one. Then, if we don't succeed, and let me think. Yeah, so if we don't succeed, we still have to mark the current one as visited. So actually we can just, no, we shouldn't do that here. We should do, well, that doesn't matter. So we can do it here, I think. We can say, okay, mark the current one as visited. We always need to do that. Now, if we succeeded, then we remember the old place that we were, because we might need to go back. If we didn't succeed, then let's make a function called pop, which takes the path. And what does it do? Or we make it a macro, then it works in general. So da pop, and it will take an array, and it will say, so first of all, we're going to use some weird feature of C now. So first of all, we should say, check that the count is greater than 0. Then we should return the last one. So actually also let me do this. It should be pointer. So let me return the last item. Okay, count. But this is not the last item. This will be outside of the array. So actually we need to decrement it first. So we do kind of a trick here where we decrement the count, then we use it to get an item out. And this kind of tuple-like thing is a weird C thing where this is like effectively, let's do it in quotes, it's effectively y, but what it does is first evaluate x, then evaluate and return, in quotes, because it's not a function call, return y. So here I can like do the assert, and then if that passes, the next thing will be evaluated, which takes an item off the top of the list. So I think that should work. Let's try to run that. So now we're stuck. Let's try to see what happens when we step. We go one back. Now it should succeed, and we go here, and we can go on our merry way, see another backtrack. And might take some time before we get another backtracking. So here we have a good example. It has to backtrack it has to backtrack twice, so we go one back, and now we go here, and then we have to backtrack some more. Then we can go in here, we have to backtrack some more. And so with this, that was weird. That was very weird. I think the array resized, but actually we have to probably, if not list contains visited current. If it's not there already, then, because that's the only way, like it's put something in twice, that's the only way it could have happened, this thing. Okay, fascinating. A lot of backtracking. Now we visited everything. Right. And probably also, like, we should do that here. If the path doesn't contain the old one, maybe we do that. Because otherwise we're gonna potentially, maybe that one's okay. But something weird happened when we reallocated. Let me just check. Probably, you know, reallocate doesn't know anything. It just takes a void pointer, which means that it should be times size of array items 0. and there we go. Because it has to be size in bytes, and yeah. All right. I want to do something else just out of interest. Let's say that we also keep a track of those things that were backtracked to, let's say backtracked from. So we'll say DA append, we'll get the backtracked, and we'll append the current one. And then we should also draw that. So for backtracked count I++, we will use the same code here. Should really get tree sitter for this setup. So backtracked. The margin is going to be slightly more, and the color is going to be slightly different. Why don't we make it red? There we go. And did not like that. So what did it do wrong? Point list, track. Ah, it's because of this. Okay, so let's see. Now we gotta trigger some backtracking. And luckily we get it quite fast. So now we get like as a red thingy. Still a bit too big. So let's make it somewhat smaller. And fortunately this one is quite good at avoiding backtrack. Oh, there we go. I think that's fine. Let's make it slightly bigger, and then we'll call it a day. So why not just twice? That makes a lot of sense. All right. Now we can do this. We can backtrack, and we can visualize all this stuff. So I think we should now, if we succeed, we need to actually remove wall between, and we're gonna get the maze, and we're gonna remove the wall between the old and the current. So this is the key of the algorithm. So remove wall between, get the maze, we'll get the old point, and we'll get the new point. Now we need to figure out which direction are we going here. So we'll say if old x plus 1 equals new x, then the direction is actually going to the right. I'm pretty sure. Okay, old x minus 1 equals new x, then it's left. If old y plus 1 equals new y, then it's actually going down. Old y minus 1, new y, it's going up. Now, depending on the direction, we need to do different things. So if we were going right, we'll do one thing. If we're going left, we'll do some other thing. If we're going up, I really should just do this and down, and that should do it. Okay, so we're going right. That means we have to remove a vertical wall. So I would like to have maybe just like set right wall, and it takes the maze and it takes a point, and then it takes a value. So we want to remove that wall. So we do like this. We haven't defined this yet. But now if we're going left, that means that here's the new point, and here's the wall, and here's the old point. We only have access to right walls, so it means we need to actually remove at the new one. And this one, since it's going up, it's probably a down wall, and if we're going up, then the down wall is, we need to remove is below the new one. But if we're going, sorry, that was correct. If we're going down, then the down one we need to move is below the old one. So then when we need these thingies, so it's probably here we put them. So set right wall, and it takes a maze and a point. We'll just call it, at, and a value, and we'll make another one like that. Now we're basically doing object-oriented programming, but don't tell anyone. And this is going to be right walls, and it's going to be add x plus add y times maze width equals value. Fantastic. And this will just do the down walls instead, but otherwise it's the same. Okay. So what happened? We went in here, we implemented remove wall between, which first finds which direction did we actually go. Then depending on the direction, we'll do different things, and I think that's pretty cool. Now we have a problem that these guys depend on the point. So I'll just put them here. So now you can see the walls are actually removed. That's so cool. And we can already begin to see the maze. And actually, to make it even more clear, I think I'm gonna do something like this. Bool draw, it's called draw path. And inside the main function, I'm gonna zoom out a bit. Inside the main function, we're always gonna do that. But this stuff, if draw path, we're going to do this, but otherwise let's not do it. And we want to be able to toggle it, so if is key released, and we'll put it on the D key for draw. We'll say draw path equals not draw path, because now we can do this. We can turn, I thought we could turn it off, but we cannot. Bool draw path equals true. If draw path, we do all that. Otherwise, still draw the maze. That's so weird. It should work. Okay, I don't know what happened, but here we go. So now I can go through a bunch of points, and I can say don't draw anything, so I can actually see the maze here. And well, we're not, and I can also step still, but whatever. We're not quite finished with the maze. So let's try to finish it. This is a bit painstaking because we don't have it automated yet. So here we go. Now we actually drew the full, we made the full maze, and you could see, let's say this is the end point, this is the start point. It's kind of nice. There's some dead ends and a bunch of dead ends, but we also guaranteed to get a path, because from this point we will visit every single point. So we're guaranteed that there is a path from this point to the end point. And there's no disconnected components or anything. Nothing is wasted with the way we set it up. So that's pretty cool. Now, let's make a function called maze_gen_step. This function will take the maze. It'll have to do some stuff with that. It will take the current point because it will have to modify that. It will take the visited. It will take the path. It will take the backtracked thing. So basically I want to put this stuff in whoopsie doopsie, I want to put that stuff into its own function. So maze gen step, it's going to be maze point list, point current, point list visited, point list path, point list backtracked, and I think that's it. Then we can just yank that here and be good to go. Now the types have changed a bit, so we need to do something like this, and that takes the maze, visited, current is a pointer, path is, so here we go backtracked, and we write into it like that. So let's see if we made any mistakes. So we didn't make any mistakes. It seems to be working. But now we can do something cool. We can say if is key released, key A for, like, let's say that's for all. So while visited dot count is less than maze width times maze height, so that means there's still stuff that's not visited. We will take a step. So we can go in now and we can press A and it will fill out the whole maze instantaneously. Let's do one more thing. Bool. So let's say animating, and that's not going to be true to begin with. And we'll say here anim frame time, animation frame time. We'll make it a cool 200 milliseconds. And if is key released, key P for play. Then we'll say animating is not animating. So we'll toggle that. And then we will say every few seconds. So time since last anim frame. Yeah, if that is greater than, what did I call it, anim frame time, then we're actually gonna do a step. And here we go, do a step. And then we should say time since last frame, probably we should say that is equal to 0. And that should also be true here. And then we should actually declare this thing. So now, if I did it correctly, we thought we could start an animation, but we cannot because we have to say if animating. We'll do this, and we should say time since last frame is actually equal to the frame time, which is a built-in thing in Raylib. And now the animation is chugging along, and you can see it's going. It's going. It's a little bit slow, but it's going. So maybe we wanna do something like if is key released key. If I click on the 1, then maybe we wanna say anim frame time is going to go a little bit. The animation is going to go a little bit slower. On the other hand, if it's 2, I'll do this. Now I can start the animation. I can speed it up, and we can even do this. It's a little bit more interesting to see how the thing is going. And now actually we should it's kind of weird that it keeps going. So what actually happens if we just let it run to the end, Because I thought it would stop now, but it didn't stop now. And something went wrong. So the visited count somehow is not updated correctly. Somehow it's not updated correctly. Maze gen step. Path old. If succeeded. If not, list contains the current, then we append the current. That does seem correct. So let's say key info, and if we ask for info, we'll say visited count is this thing, and it's going to be visited.count. And we'll go over here and we will run the animation for a bit. I can stop it again just to check. Great. So now, what is the visitor count? The visitor count is 100, so probably maze width, maze height. No, that's all. So sorry. Okay, so if it's animating, it's because we need this check. We need this check. We have to say if. Okay. There we go. So now we run it. We run it very, very fast, and it should stop now. Stops animating. Great, and the maze is done. All right. I think that's pretty cool. That's pretty cool. Let's make a big maze. Bigger maze anyway. Probably that doesn't look too good. Let's run it. So it seems quite slow, but it's only slow because we're animating it. I'm pretty sure it could do it instantaneously. It is doing a lot of backtracking, and I don't know if there's any way to skip that. But you can see it makes a quite cool maze. And then maybe you can generate mazes like this, and you can use them for something else that's interesting. So here just instantaneously ran through everything, and you can see. It is a new thing. So maybe we just want to say, okay, if is key released and is key R for restart. First of all, we're going to turn on all the walls. We're going to say DA empty. Actually, let's just not make something for that. Let's just say current X is 0, current Y is 0, visited dot count is 0, path count is 0, and backtracked count is 0. So everything is reset. And now I can do this. I can reset it, and I can draw like a bunch. And you can see that it ends up being different every time. So I think that is pretty cool. Something we can do for fun is something we won't do now. But so here we have it. The video is pretty long, I think. But here we go. Algorithm for generating a maze with animations and everything. And I hope you like it, and I will see you in the next one.